Now, next issue for us will be the circumference of this same curve. So now, just right now, we calculated this enclosed area, just for your information, because it took quite a while. So this area has been calculated to have a value of 6 times Archimedes constant pi. That's our result. And now we want to know the circumference of the, you know that the black curve, of course, includes also this blue segment. I just couldn't, I just didn't draw it in 2 different colors. So please don't be confused. The black curve refers to the whole object. Now, what's the circumference? And this is a very good opportunity to solve a so-called scalar path integral. More exactly speaking, it will be an integral where we say the function, this way, the function t1, t2, the scalar function f of t, which we sum up continuously along the curve. And as you know, there is always a certain substitution performed by taking the tangent vector. In this case, its absolute value is sufficient, and then integrating for t. That's roughly speaking the way you construct a scalar curve integral or path integral. I'm sorry, I should say x dot vector of t and then over dt. So, and then it turns out in the special case when this function is just taken to be the so-called one function, okay, which is just constant for any value of t, or you could also say the neutral function. In this case, we just can wipe it out, and we will find that this is the most easy method to calculate the length of the curve. Why? Because this is, you might say, a speed vector. This is sort of the length of the tangent vector summed up along the curve. And so infinitesimally, we get little tiny pieces of this curve, including their length, summed up along the curve, which results to be the total length of this curve. So that's quite an interesting concept behind. And that's what we'll do right now for being concerned with that vector field and its possible potential. So like I told you, it's quite, the first exercise is quite a long task. So this is just for your control. If you had a look on Wikipedia about asteroid curves, you will find the general formula that the enclosed area will be 3/8 times pi times e squared. And this a is a parameter usually used instead of this prefactor, our prefactor, which is equal to 4. You know what I mean? So in Wikipedia, I didn't open the page right now. You will find something like x of t, x vector of t will be a times cubed cosine of t cubed sine of t, you know? And in our special case, we used a to be equal to 4. Now just insert this here. You will find 4 squared equals 16, then shorten 16/8 equals 2. So 2 times 3, which is 6, and in the end it equals 6 times pi. So our result is correct. This is the more general result for different scalings. That's just nice to know that we are consistent with informations in books. So that's everything correct. Now, the circumference. I used the German symbol usually taken for the circumference. That's why. That's because it's called Umfang in German. Please, I don't know what's usual in English. Anyway, it's called U. So, and now I am allowed to use this symbol of a closed integral. You know what it means? It means that it takes place along a closed curve. So that's nice to know and nice to use. And our path 1 is a closed curve. That's why I symbolically write it down this way. And then, as I told you just before, it's necessary to take the absolute value of the tangent vector, x vector dot of t, which we already know from differentiating radius vector functions. And please understand why it's allowed to take the absolute value. This is simply because the direction along the curve does not play any role. We just are interested in the length of our curve. So that makes things a little bit easier. There's no scalar product to be taken with a vector field or something. The whole operation here is a scalar way of calculating and proceeding. So what is it? But then also, please don't forget to take the derivative first of all, and then building or constructing the absolute value. So step by step, what is x vector dot of t? And now, for certain reasons, because I tried both ways, I recommend you and me to switch over to this transformed expression, right? So we might use this again, no problem. The chain rule, you know, by differentiating 3 times, then we would get 3 times cosine squared of t and then times negative sine of t. It's not even harder necessarily, but no, let's just try and use this one directly this time, okay? So, oh, do I? No, I don't. We have been using this one for the enclosed area, actually. Now I switch back to that one. Yeah, okay, you can try both ways. So I'm sorry, but actually I'm using this one. And now, of course, the derivative of the first component will be 3 times by the chain rule, okay? 3 times cosine squared of t, this is the potency rule I'm using, and then times the inner derivative, which is the derivative of cosine of t equal to negative sine of t. You remember? And can verify that this is what I'm doing here, okay? Sorting things up, then we get negative 3 times cosine squared of t times sine of t. The same thing for the second component. Remember, it was originally, don't forget the scaling factor 4 also outside, right? But here it was sine cubed of t. And the derivative of sine cubed of t, of course, this time is 3 times sine squared of t, and then taking the inner derivative times cosine of t. So there's no minus sign here. Here it's positive, here it's negative. And that's it. And now take the absolute value the usual way by using Euclid's matrix, as you all know. Okay, so that means I have to build or to construct the squared sum of these 2 components and then take the square root of this. Also, all the time keeping this or leaving this factor of 4 alone. Here it is still, okay? Now, some more things to consider. Well, first of all, what's the square of this first component? Well, that's easy. The negative gets squared away. 3 squared equals 9, here it is. And then we get actually the cosine power 4 of t. Here, you know, the square of the squared square equals power 4. Due to potency rules, and then also times the sine squared of t. First contribution. Summing up plus the square of this one. And as I said, I'm constructing the squared sum of the components. So next contribution is plus 9, 3 squared, times this times sine power 4 of t, yeah? And then times cosine squared of t. So here, under the square root sign, you see the squared sum of the components. And then I take the square root. Why? Because I'm interested in the absolute value of this vector. So that's the usual Euclidean metric, right? I should perhaps write it down. Euclidean metric. I could also say Pythagoras theorem, but this is the best way of coining it. Anyway, because that's the way of distance measuring we use in our Cartesian coordinate system. So this is just a continuation point. So the whole expression is 1 square root of the whole term. Okay. Now, please look at the blue color. For special reasons, it's let's say it the following way. In general, it's a little bit dangerous to perform an integral which extends over certain singularities. You see, starting here, I would just integrate, sum up, singularity, 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 and then so if you can avoid it, you should avoid it. And this is a really, I know this is not a very precise formulation now. Well, it turns out if you don't take care and you just take the integral over the whole curve from 0 to 2 pi, you might get a wrong result. You might even get 0 as a result. So this takes some time to more precisely reason around. So reasoning why this is necessary or makes sense would take a little more effort. Let me think. Well, behind what we're doing here, you know what we do? We just simplify the whole procedure. And now you will quite surely agree with me that the shape of this curve is very, very symmetric. It has a high degree of symmetry. So you see, there is an axis symmetry to the x-axis, to the y-axis, and even it's quite obvious that all these 4 branches here have exactly the same shape and length. So it's at least it's not forbidden to say, okay, let's just take the integral only from 0 to pi half. Okay, you can guess that for t, this is the value of 0, then pi half, pi, 3 pi over 2, and 2 pi. So like corresponding to 0 degrees, 90 degrees, 180 degrees, 270 degrees, and 360 degrees, because it's just, you could say it's a modified unit circle, right? By taking the cubes of cosine and sine. Anyway, it turns out that the blue section here, which is by chance also the so-called path P2, is sufficient. Now, a big advantage of this method, I can tell you, is we restrict ourselves to the first quadrant, right? Where x and y coordinates are not negative, they are non-negative, and that's always, of course, an advantage in calculating. So I hope you agreed with me. It's allowed, and it makes sense to integrate only from 0 to pi over 2, and then but multiplying the result with an additional factor of 4. So this gives us the total length of the curve. And now, please note that this is the scaling factor from before, and this one is newly introduced. So altogether, I get 4 times 4, which equals 16 for now. Also, this is really an advantage, as I see, because by taking the positive square root, well, I must say all these terms with their even exponents are positive anyway. But now, that's the question, how to argue. Oh, is that true, what I'm saying here? Yeah, wow. Sorry, I forgot a very important step. But in the end, when we take the square root, it's really necessary to argue that the terms inside, and I'm talking about sine of t and cosine of t, could theoretically be negative, but then squaring these and taking the positive square root would result possibly to a false plus or minus sign. And so it's very advantageous to reduce ourselves, to restrict ourselves to the first quadrant where cosine and sine of t are both positive, which they are, since this corresponds to the x and y coordinate of the asteroid curve. So I'm sorry for this complicated consideration, but it's really necessary. Shortly, in the moment when we take the square root. Otherwise, I would have to use absolute value signs here and here, and this would make things more complicated. And that's the reason why, if I integrate from 0 to 2 pi, I would have much more special cases to consider, and then in the end, I would get the correct result. But just leaving this whole problem away by using that trick, just described, taking 4 times the segment in the first quadrant, all these absolute value considerations just go away, and it gets much simpler. So that's the true reason why I'm doing this. And it has not really anything to do with the cusps or the singularities, as I stated before. These are a problem only when differentiating, not when integrating. So I'm sorry for this little lapses. Okay, just follow my transformation out, because that's important. It's very dangerous to make the wrong transformation at this point. What do? I tell you, I recognize, you know, that's really dangerous. If you think, this is a squared sum of sine and cosine again, and I can put this in parentheses, and now I tell you, no, you can't. If you try and put these two, as the sum of these two in parentheses, it's just not possible, because this factor here and this factor here, they are different, okay? Because they are different, you cannot put the sum of these two in parentheses. So what I'm doing here, it looks alike, but it's quite something different. What I'm doing is the following. I register, or I recognize that, look here, inside here, there is also a cosine squared of t. And here inside, there's a sine squared of t. And now, taking these outside, what remains of this term and of this term will be the same. It sounds complicated, but I'm sorry, it is a little complicated. So first of all, take the factor of 9 outside, and then just draw the square root of 9, which is 3. And that's the reason why I have an additional factor of 3. Look, 4 times 4 times 3 would be 16 times 3, which is 48 altogether. I draw all these factors together to be 48. Can you follow me? The square root of 9 is taken outside. So just ignore the factor of 9, it's gone, right? But then I taking a cosine squared of t outside here and putting it in the parentheses, this place, what's left outside is cosine squared of t times sine squared of t, of the first summed in this. These are two terms summed up, okay? In the second expression, I take a factor of sine squared of t outside of this, okay, and put it in the parentheses next to the cosine squared of t. What remains then is here sine squared of t times cosine squared of t again. So you see what I'm doing? I'm just taking, it's the same thing as trying and combining these two, but I don't. I have to take them from here. And then I get my squared sum of cosine and sine inside the parentheses. What's left outside will be the same expression in both cases. And that's why it's allowed to do it this way. So this can be replaced by a factor of 1. And what remains is the cosine squared of t times sine squared of t. And then the square root. And now this is simple, taking the square root of cosine and of sine, and just everything that remains is the product of cosine of t times sine of t. And this is really the dangerous moment. And I can explain you again. Just a numerical example. Imagine you have a -7. Oh, I'm sorry. Yeah, -7. So then what do? You square it, and then you take the positive square root. You know that this is always the positive square root. So the result will be equal to square root of 49, which is definitely equal to 7, not plus or minus 7. This is what you do when solving quadratic equations. But in this case, this is correct. So taking a negative number, squaring it, and then taking the square root gives you a positive number. And that's why, in general, it's just not allowed to do things like this, like saying square root of a squared is simply equal to a. That's plain false. It may be correct if a is positive, but if a is negative, it's wrong. So that means the correct transformation is taking the absolute value. And this is what we would have to do here if we had not restricted ourselves to the first quadrant. So now, I hope now it's clear why I'm doing so. In the end, we are on the safe side now. We can say 48 is what we get times, and then just integral cosine times sine. This is really a standard integral. We don't have to solve it again. We can look it up in a handbook. and we will find that the primitive function will be 1/2 sine squared of t, and then we have to evaluate it between 0 and pi over 2, remember? And that's nice because you know that the sine of pi over 2 equals 1. This is its first positive maximum, maximum in the positive domain. So we have a factor of 1/2. We can also draw this outside. 48 over 2 equals 24. And then in the parentheses, it remains 1 squared minus 0 squared for the lower bound, right? So it's just that, it's 24. That's the circumference of the asteroid curve.